Good morning, boys and girls, and welcome back. Today we're going to talk about polar coordinates and their graphs and tangent lines to polar equations. Alright, so let's do a little quick review of polar and what polar is in the first place. If we want to talk about a point in space, again, we generally use the coordinate plane, which has, some distance x in pink here, that we go left and right, and some distance y up and down, and we talk about the point xy, right? Now, another way we could refer to a point in space, though, is using our polar coordinate system. If I want to talk about where this point is out in space, another way I could do it is I could talk about the radius, how far away it is out from the origin, and then I could also talk about the angle up, which is at. So r and theta. And we describe a point this way, hey, it's some angle and some radius out, then this is our polar coordinate system. When you see a point in polar, again, it's always r comma theta. However, when you graph them, I think about it the other way around. I always do my angle first. I go to that theta, and then I go out some distance r. If r is positive, you're going forward. If r is negative, then you would be going backwards. That'd be like a negative r, and I'd go in the opposite direction. Okay, so if we want to convert back and forth from these two different ways of talking about points, you're going to need these polar conversions here. X equals r times cosine theta, and y equals r times sine theta, and then r squared equals x squared plus y squared. So these will help you convert from polar to rectangular coordinates, or Cartesian coordinates as they're called, and back and forth. Okay, let's talk about some common polar graphs that we should be aware of. If you have theta equals some number, theta equals a, theta equals pi over 4. This is going to be the graph of a line. If my theta is always the same, if the angle is always the same, I go to pi over 4 and it's always the same, then it doesn't matter what my radius is. I can have a bunch of different radiuses. And so like theta equals pi over 4 would be the same as the line y equals x. Okay? So that is one way that we can get lines, is just theta equals a number. And that's the way we will get lines, is theta equals a number. Okay, our next type of common graph is a circle. And so here's the three different ways we can maybe end up with a circle. If I get r equals a, it doesn't matter what my radius is. R always equals the same number. R equals 2. Then I always have a radius of 2. And so that would give me a circle centered at the origin. All right. If I have r equals a sine theta, if you remember back to our unit circle, sines were the y coordinates. The sines kind of go up and down. If I have r equals a sine theta, then it's a circle that is shifted up like that. A, in this case, is going to make your circle bigger or smaller. And if it's positive, it's on top. And if A was negative, then it would be on the bottom. All right, and cosine was like our x-coordinate on the unit circle. So cosine for those circles are going to be along the x-axis. And so same idea here. If A was positive, it would be to the right. If A was negative, it would be to the left. And so that's what, again, A makes the circle bigger or smaller. So these are three different ways that we can get circles that we need to be familiar with. All right, the next common type of graph we need to be familiar with is roses. Roses, remember, are the ones that look like flowers and they have petals on them. And they're in the form of r equals a sine n theta or a cosine n theta, where this part is inside the parentheses here. And they look something kind of like this. Some of the roses look something like that. And where a, again, is the length of the petal, and then n, if n is odd, you're going to have that many number of petals. And if n is even, then you have 2n petals, right? So like here, my n was 2 because I have 4 petals for the red fun. N is 2. And then here, because I have 3 petals, my n is 3 because I had 3 petals, all right? This is a sine one, and that is a cosine one. And again, there is some relationship between the x and y. But for what we're doing here, just again, if you just know roughly we're dealing with a rose, then you're in good shape. And the last one we have to know and be familiar with are limacons. Limacons, again, we have a few different types, but they're in the form of a plus b sine theta or a plus b cosine theta. R equals a plus b. And these were, again, the different types that we dealt with. If A is less than B, then you got the loop on the inside, kind of like right here. And again, if the loop is up and down, this is a sine one. This would be like a negative, sine one. If A equals B, then you get like a heart-shaped graph, which this has a special name. We call it a cardioid function. And again, if the heart's going left and right, now that's a cosine cardioid. So that's kind of how we can tell the difference between sines and cosines. And if A is bigger than B, then you get it's kind of like a dimpled circle. We call it. It doesn't go in quite as much as the heart does, but it's kind of dimpled, and it looks something kind of like that. Okay, or dimpled graph, dimpled limacon. There was one other one you talked about back in pre-calc called the lemniscate, but we really don't deal with that one much in here. But you can go look that one up if you want to. But these are the main ones that you want to be familiar with, mainly against circles, roses, and limacons, these different ones. They'll be the main graphs that we deal with here in calculus, and it helps, again, when you see a polar equation, if you kind of know roughly what it looks like. Okay, and to find the slope of a polar function, again, slope is dy dx, and so to find dy dx in a polar function, I'm going to have to find dy d theta over dx d theta. And so you would have to take the derivative of y with respect to theta and x with respect to theta, going back to these original equations we had over here, our x, y conversion ones. And then if you divide those, you'll end up with dy dx. All right, so let's give this a go here. And let's find, given r equals 1 minus cosine theta, let's find the equation of the tangent line at pi theta equals pi over 2. Again, not super necessary in this problem, but just to kind of practice a little bit, in this case, this is in the form of r equals a plus b cosine theta, and a and b are the same. They're both 1, so this would be a cardioid, and that's about as much as you would need to know about this graph to kind of help you get through it a little bit, to get yourself a picture. In this case, we want to write the equation of the tangent line, so just like we've started all year, I need a point and a slope, and when we write the equation of the tangent line, again, we're doing it on the Cartesian plane, or the coordinate plane, so I'm going to need an x and a y, and then my slope dy dx, okay? Those are what we're going to have to find here. All right, so let's start by finding x. Remember that x equals r cosine theta in our polar conversion, and then so I know r is 1 minus cosine theta, so x would be 1 minus cosine theta times cosine theta, and now we want to evaluate this at pi over 2, so x is 1 minus cosine of pi over 2 times cosine of pi over 2, which is 1 minus 0 times 0, which is going to give us 0. So now I know my x coordinate is 0. And now let's do the same thing with y. Y is equal to r sine theta, so y is going to be equal to 1 minus cosine theta times sine theta. And again, now when you evaluate that at pi over 2, we're going to get 1 minus 0 times 1, or 1 times 1, which is 1. So our point on the Cartesian plane would be x comma y, or 0 comma 1. Now we need to find dy dx. And to find the slope of dy dx, again, that's going to be dy d theta. We take the derivative of y with respect to theta, and then divide that by the derivative of x with respect to theta. All right, so to find dy d theta, because these are being multiplied together, I need to use the product rule. So the derivative of negative cosine, the derivative of 1 is 0, derivative of negative cosine theta is sine theta, times sine theta, derivative of the first times the second, plus the first, 1 minus cosine theta, times the second, times the derivative of the second, cosine theta. And so we get sine theta times sine theta plus 1 minus cosine theta times cosine theta. And again, I want to evaluate this at pi over 2. So at pi over 2, sine of pi over 2 is 1 times 1 plus 1 minus cosine of pi over 2 is 0 times cosine of pi over 2 is 0. So I get 1 plus 0, or dy d theta at pi over 2 is going to be equal to 1. So now I just need to find dx d theta at pi over 2. So to find dx d theta, again, I can take the derivative of x up here, of my 1 minus cosine theta times cosine theta, using product rule. And we're going to end up with sine theta times cosine theta, plus 1 minus cosine theta times negative sine theta, derivative of the first times the second, plus the first times the derivative of the second. And now I want to evaluate that one again at pi over 2. So this is 1 times 0 plus 1 minus 0 times negative 1. So I get 0 plus negative 1, which is negative 1. Alright, so dy d theta was 1, and dx d theta was negative 1, so my slope is negative 1. Now that I've got a slope and a point, I can write the equation of the tangent line. Y minus 1 equals negative 1 times x minus 0, or just times x. And there is the equation of our tangent line. Okay, number 2, we want to find the horizontal and vertical tangents for r cosine theta on 0 to pi. Alright, just getting our mind frame. R cosine of theta, what kind of graph is that? Well, r equals a cosine theta is a circle, and we said it would look something kind of like, to the x side. So this is going to kind of look like that. And so we're going to look for the vertical and horizontal tangents on this graph. Right? These guys right here, right? That's where our vertical and horizontal tangents would be. So obviously to find these, we're going to want to look at the slope of the tangent line. And to find the slope of the tangent line, we're going to need dy d theta and dx d theta. And to find dy d theta and dx d theta, I'm going to need x and y. So I'm going to start right here with these. So x would be cosine theta times cosine theta, since r is cosine theta, or cosine theta squared. And so when I find dx d theta, we're going to get 2 cosine theta to the first, chain rule times negative sine theta, or negative 2 sine theta cosine theta. Alright, so there's my dx d theta. Now I want to find dy d theta. So again, since r equals cosine theta, y is cosine theta sine theta, and to take the derivative of this, I'm going to now need to use product rule. So, derivative of the first, negative sine theta, times the second, sine theta, plus the first, cosine theta, times the derivative of the second, cosine theta. And we get dy d theta equals cosine squared theta minus sine squared theta. Alright, and I had to slide over there a little bit. Now, what we need to do is, again, I'm looking for the horizontal and vertical tangents. So, again, the slope of the tangent line is dy d theta over dx d theta. And so what I'm going to need to do is, if I want a horizontal tangent line, that's got to equal 0, or dy d theta is going to have to equal 0. So it'll be horizontal when dy d theta is cosine squared theta minus sine squared theta, when that equals 0, or when cosine squared theta equals sine squared theta. And on the interval from 0 to pi, that would happen at pi over 4 and 3 pi over 4. So those are my two theta values. So we found those theta values, but I want the whole point. And remember, the point is r comma theta. So I need to plug these thetas back into r. So cosine of theta, cosine of pi force is root 2 over 2. And my theta was pi force. And the other point is going to be cosine of 3 pi over 4, which is negative root 2 over 2, comma 3 pi over 4. So those would be the points of my horizontal tangents. And now where to find our vertical tangents are at. We get vertical tangents, again, when the slope is undefined, or when dx d theta is going to equal 0, and dx d theta was negative 2 sine theta cosine theta. And so this is going to equal 0 when theta equals 0 and pi for the sine half of stuff, and at pi over 2 for the cosine part of things. So when theta is 0, pi, and pi over 2 is when we're going to have vertical tangents. And again, we need those points, r comma theta. And we have the theta, so now we need to find the r's. So I'm going to plug those in and get my 3 points. If I plug in 0, I get 1, so 1 comma 0. If I plug in pi, cosine of pi is negative 1, so we get the point negative 1 pi. And when theta is pi over 2, that is 0, so 0 comma pi over 2. The only thing you'd want to watch out for, so these are the points where our vertical tangents are at. The only thing you would want to watch out for here, though, is if both dy d theta and dx d theta were 0 at the same spot, then we would not be able to tell if it's a horizontal or vertical tangent. Alright, boys and girls, that's it for today. Come see me if you got questions. See you later.